Hey all, welcome back to Organic Chemistry Lab this semester with Tara and Ray. Before we get into the experiment, I'd like to refresh general safety. Make sure you always come to lab prepared. Do not wear baggy clothes and always have your hair tied. Here you can see Tara coming into the lab with a baggy sweatshirt and untied hair. And also always have pants and closed-toe shoes, as Tara has here. To be properly prepared, come to lab with clothes that fit well and cover your skin. If not, please bring a lab coat, but remember it is optional. You also need lab goggles. If you have long hair, please tie it up, as Tara is doing right now. Scarves are okay, but ensure that they are worn tightly. Before starting the experiment, remember to check your lab notebook and make sure everything is written. Once ready, grab a pair of gloves before touching any chemicals or glassware. Here, you can see Tara putting on her gloves before starting the experiment. Fire safety. Remember, if there is a fire, the front of the room contains a fire extinguisher and fire blanket. Also, Tara is going to show you the spill kit if there's any spills in the lab. If you get any chemicals on you during the lab, it has an eye wash which is activated by pulling it down. If any chemicals get on your skin, there's a safety shower right by the eye wash. There is a curtain for your privacy. If you break any glass, don't fret. Call your TA over and they will assist in cleaning it up. Notice Tara is brushing directly into the dustpan, ensuring to get all large glass pieces into the bin. Notice she also cleans the floor. And notice she is not kneeling directly on the ground. That is to ensure she does not get any glass shards on her clothes or self. Once everything is swept up, she will go to the glass waste disposal area and dump it away. Once disposing the glass, Tara takes the dustpan and brush and puts it back down. Now let's start with our third lab this semester, distillation, where we'll cover simple and fractional in 2 parts. Let's start with simple distillation in part 1. And a quick introduction, just to refresh you guys on some concepts essential for this lab. Distillation was found to exist as early as 1200 BCE for the creation of perfumes in the Byzantine Empire. Distilled water was also extremely commonly found in written records due to the need of purification of salt water for drinking water. Also, it was found medieval Muslim chemists widely explored the uses of distillation, finding uses for ethanol extracted from wine. Today we use distillation to generate a multitude of products such as perfumes, alcohol, and food scents and flavors. So how does distillation work? We have to review a few topics. First, vapor pressure. Here I have displayed a vapor pressure curve. You can clearly see for each compound that as temperature goes up, so does its vapor pressure, which is shown on the y-axis. Once the liquid's vapor pressure reaches atmospheric pressure, noted by 760 millimeters mercury, any increase above that will result in the liquid becoming a gas. It is also important to note that we are looking at these as individual compounds. We will talk about a mixture a bit later. So, what happens to the boiling point of a mixture? To better understand that, we have to look at Raoult's law. In the 1800s, a French chemist by the last name of Raoult showed an ideal case that the partial pressure of each component of a mixture of liquids is equal to the vapor pressure of the pure component multiplied by its mole fraction in the mixture. So, we can also say that as a result, when a substance is dissolved in a solution, the vapor pressure of the solution will generally decrease. It is important to note that this relies on two things: the mole fraction of the amount of dissolved solute present and the original vapor pressure. Now let's look at Raoult's law mathematically. So we can say Raoult's law as an equation where Pt equals P star T times X of T. Now what does that all mean? We're going to have P of T equal the partial pressure of component T in the mixture. P star T is equal to the equilibrium vapor pressure of the pure component T. And then we have Xt, which is going to be the mole fraction of component T in the mixture. So with this knowledge, let's look at a solution of mixed volatile liquids, T and C. Here we can say that P equals the total vapor pressure of a solution, and that will be Pt plus Pc, which we can rewrite as shown on the screen above. One thing to note is that this is for liquids. We have to also take a look at vapors or gases. So if we're going to look at gases, we're going to have to look at Dalton's law. And Dalton's law, which was discovered in 1801 and is based upon the kinetic theory of gases. Here, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressure of the gases in the mixture. We can derive this through the ideal gas law, where PV equals nRT. This we can rewrite N, total, of the sum of molar values of gases in the mix. This allows us to rewrite the ideal gas law as P total V equals N total RT. We can use this equation to find the mole ratio of X of I, where X is the mole ratio and I is a specific compound, by substituting below. So we can say where pressure of compound I divided by pressure total is equal to the mole ratio of I. This is shown for N and V as well. We will take advantage of pressure as we already have vapor pressure values. So why do we care about Raoult and Dalton's law? In essence, distillation, we are taking a mixture of liquids and heating them to generate vapors. We will try to separate them by heating the mixture and hoping one becomes a gas while the other stays as a liquid. The gas will move to another portion, the condenser, and be chilled and go back into a liquid in a different vial. The knowledge of vapor pressures and mole ratios become important as we want to ensure we have a pure separation. Essentially, while distilling our sample, we will be generating this curve shown on the screen, where the sum of various mole percentage will generate a vapor pressure to become a vapor or be below atmospheric pressure and stay as a liquid. We take advantage of this relationship and temperature to separate these compounds from each other. Your TA will talk in more detail about the steps that you can take to ensure a pure product by the term theoretical plates. So in order to make use of that graph, we will need to know the mole percentage of mixtures. To do that today, we will be using a refractometer to assist us. This instrument measures the index of refraction, which is calculated from Snell's law. You have learned about this in high school. For example, the way light passes through air and water is different. That is why you observe a pencil bending if you are putting it into a glass of water. This refractometer will measure the extent of light that is refracted of transparent liquid or solid substances. This refractive index can be used to determine the sample's purity or concentration of substances dissolved in the solution. This index is gotten from getting the refractive index through a calculation from the ratio of the speed of light in a vacuum to that in a second medium of greater density. A refresher on Snell's law. This is when N, which equals the refractive index, and theta, the angle of light refracting through the medium. One medium is known and generally is either air, water, or a vacuum. The formula is listed below, where n1 times sin of theta of 1 equals n2 times sin theta of 2. You can look at the image to see how they correlate to each other. Your TA will go in more detail on how to use the refractive indices to calculate the percentage of each compound in the mixture. So let's take a look at the Abbey refractometer that we'll be using today. So it looks a little bit like a microscope. So one you may notice at the top, there's an eyepiece. Essentially, you look here to make any adjustments that are needed and read the refractive index. Then you'll notice the sample prisms and they're hinged. So there's a upper sample prism and a lower sample prism. And this is where you're going to put your sample. Then there's the light source. So this provides light for your sample. It's on a movable arm, so you can swing it out of the way when you place your samples on the prism. One thing to note, we're going to be using sodium D line for our light, so the light of one wavelength. Then there's the light source swivel arm lock. So this is essentially a slotted nut that works itself loose as you move the light source up and down a few times. Then there's the sample and scale image adjustment knob. You use this knob to adjust the optics so that you can see a split field in the eyepiece. I'll go over that with some images. The refractive index scale also moves when you turn this knob. Then there's a scale/sample field switch. So essentially, you will press the switch and basically the numbered refractive index scale will appear in the eyepiece. And then when you release it, you'll see your sample in the eyepiece and you can adjust it. So I'll show more details with some images. So as we know, the refractometer works based on critical angle. So the sample is placed between two prisms, which you can see on this image, measuring and illuminating. Light enters sample from the illuminating prism at the bottom, gets refracted at critical angle at the bottom surface of the measuring prism, and then the telescope is used to measure position of the border between the bright and light areas, which you can see in the top right corner. The telescope reverts the image, so the dark area is at the bottom, even if we expect it to be in the upper part of the field of view. So knowing the angle and refractive index of the measuring prism, it is not difficult to then calculate the refractive index of the sample. Surface of the illuminating prism is matted. Why? So that the light enters the sample at all possible angles, including those almost parallel to the surface. However, there's a little bit more that I have to talk about. So, as we know, refractive index of a substance is the function of a wavelength. If the light source is not monochromatic, and in many devices it rarely is, light gets dispersed and shadow boundary is not well defined. So in that upper right image, that basically dark portion, that's the shadow boundary. So instead of seeing a sharp edge between the white and black, like what we see in that image, you'll actually see a blurred blue or red border. So that means that the measurements are either very inaccurate or impossible to take. So to fix this, in the ATTIRE refractometer, there are two compensating Amici prisms in the design. So the telescope position can be changed to measure the angle. Also, the position of the Amici prisms can be adjusted to correct for the dispersion. So the result of that will have the shadow edge being well defined and easy to locate. So now that you've loaded your sample on and you've put on the light source and closed the prisms and you're looking through the eyepiece, on the top image, you're going to see that shadow boundary. Notice that there's a vertical X in the center. Your goal is to make sure that the shadow boundary is at the center point of that X. Without that, you will not have an accurate reading of your refractive index. So the first step is to make sure that it's not too high, not too low, and once in the center. Once there, you can press the switch that will then put on your refractive index reader. So this is the scale. And in the bottom image below, you can see the scale. So this is going to show up and you're going to read the point marked at the center of the X. So here you can see that it's right before 1.440. So this is accurate up to 4 decimal places. So when reading this, I would read this at 1.4398. Why am I getting to that value? So there's 3 sizes of dashes. The largest dashes will have a number on them. The second tallest dashes signify 0.1 deviations from that large number, and then the smallest dashes signify deviations of 0.05. So at the position of 1.440, the smaller dash right before it signifies that it's at 1.4395. And as you notice, our X is in the center in between those dashes. So you can approximately read that this is 1.4398. And that's what you would record for your refractive index. It's also important to note that the refractive index changes with temperature. So when you're using this, make sure to record the temperature, which is on the thermometer to the right of the instrument. Also, it's important to note that volatile samples require quick action. So, if you're working with something known to be volatile, make sure you take your rating extremely quickly. So, for example, cyclohexene has been known to evaporate from prisms basically more quickly than you can obtain the index. So, it may take several tries as you readjust the light, turn the sample, and scale the image, and whatnot. Also, one thing that's really important is you have to make sure that the instrument is level. If the instrument is not level, the organic liquids can actually seep out of the jaws before you're ready to make your measurement. Thus, you would be just getting the refractive index of air. So, these instruments are known to be extremely accurate. How do they keep them so accurate? So actually, these instruments are calibrated rather consistently using a set of samples to generate a calibration standard curve. So these samples have a known refractive index, and they will then be loaded onto the instrument and then used to help calibrate it afterwards. So it's very important that this is known because this is why your values are so accurate. Now let's go over some safety for this distillation lab. Please be careful with the hot plates. The cord can easily melt if it's on the hot plate. Another thing is methanol and isopropanol. Both are flammable and toxic through contact with skin or ingestion, especially methanol, which can cause blindness. And be careful with the glass pipettes. They can break rather easily and cause punctures if mishandled. Please be careful. Now let's start off with some simple distillation. Here, Tara is preparing her mixture. She has her round bottom flask in a holder and is adding boiling chips to the flask. You'll see in a moment that she was going to use the graduated cylinder to measure out both the methanol and isopropanol. Remember, she is adding 1.5 milliliters of methanol and 6 milliliters of isopropanol to the flask. You'll notice that she does not mix in the graduated cylinder. She measures each compound individually and adds it to the round bottom flask before mixing in that flask. This is due to molecular interactions between the compounds, which will occur if mixing in the graduated cylinder. This will actually throw off the volumes when measured, giving you a different mixture, thus throwing off your calculations for this lab. Notice once she mixes it, she parafilms the flask. These solvents are volatile and can evaporate readily. She's going to set up her apparatus. But before that, she's taking out her half a milliliter in order to collect the refractive index on it later. You will notice she's using a graduated cylinder to measure everything accurately. Once she has done this, she will transfer it to a labeled vial to ensure that she does not confuse this sample with all the other samples that will be collected. So let's go over the pieces that are going to be used today. So you've already seen the round bottom flask. To that, we're going to attach the distillation adapter. On top of that goes the thermometer adapter. To the other part of the distillation adapter goes the short condenser, and then finally at the other end, the vacuum adapter. Ignore the fractionation column for now. The thin wall tubing is used to connect to the condenser. There will ensure that water is constantly flowing in and out to maintain the temperature so we get proper distillation. The wooden blocks are to raise up the hot plate in order to allow for us to collect our sample into a graduated cylinder. Here you can see everything put together. The tube is connected to the distillation apparatus, and then the thermometer adapter is on top, allowing us to record the temperature. Then the condenser is connected to the distillation apparatus, which is then connected to the vacuum adapter, where we can collect our sample. As you notice, the tubes are going water in at the bottom, water out at top. That's to ensure that we have a constant flow of fresh water in and nothing gets stuck. And notice how everything is rested in the aluminum block and held with clamps. Without the clamps, everything would fall apart. You'll see this put together in the next part of the video. Here, we will watch Tara set up the simple distillation apparatus. It is important to note that she is using clamps to ensure that her setup is secure and will not fall. We do not wish to break our glassware. Also, note that the vial is currently covered with parafilm. Remember, both solvents are extremely volatile and will evaporate over time, changing their composition of the mixture. You can also see that her condenser has two tubes. One she is putting in the sink and one that is connected to the actual sink. Here you can watch her screw on the rest of the attachments while setting up the simple distillation apparatus. Here we're going to watch Tara correctly fill the condenser. Remember, the water in is at the bottom, and this is essential to ensure proper flow and to ensure that the condenser remains at the same temperature throughout the experiment. Also note, the water out is going from the top into the sink. You want a strong flow to ensure that the condenser remains at the same temperature the entire time. Now Tara will start the distillation by heating the sample. It is important to know the boiling points of your compounds, as this will determine what temperature you will heat your sample at. This is why we asked this question during the pre-lab. The physical properties table is essential to properly set up many of your experiments. Please ensure you always complete it. Now we are watching the experiment go forward. You can see the sample is boiling and we are monitoring the temperature. We then check to see the volume that's been collected. You can see it's slowly increasing. Once we reach 0.5 milliliters, Tara will quickly collect the sample because these solvents are volatile and can evaporate, so we do not want to change the composition. She quickly uses a glass pipette to transfer it to a labeled vial and seal it. Once collected, she quickly puts the graduated cylinder back in order to continue collecting distillate. The experiment will continue, and we will take the temperature at every 0.5 ml of distillate. Here, it has finished. Now that the experiment is finished, we must properly break it down. Please follow what Tara is doing. Notice she is emptying the condenser first. That is to ensure that there is not a mess. Notice how she holds it high to allow the water to flow out properly. Once emptied, she puts the condenser to the side. The rest of the breakdown is pretty straightforward, removing all the tubes and breaking apart the apparatus. Now that our sample is collected, let's go over using the refractometer. Your sample, a light source, a knob to adjust the refractometer, and a thermometer. It's essential to record the temperature as the refractive index is based on the temperature of the location. And there is the light switch. Here you can watch Tara load the stage. She lowers the light source and opens the stage and puts her first sample, pure methanol. She ensures it's filled and closes the stage. Then puts up the light source. Once the switch is on, she can look inside and then adjust the refractometer. Here she's adjusting it. Let's wait and see what we can see inside. Our goal here is to ensure that the black line is at the center of the lens. Once it's at the center, we can read our refractive index. Here Tara is just making sure that it's centered. You turn off the light source in order to read the refractive index. When she ensures the number, she will then clean the stage. Remember to lower the light source and then open the stage. Always turn off the light source. And when you're cleaning, always use a Kim wipe, never paper towel, because paper towel will leave fibers. And you want to use a Kim wipe to ensure that the stage is completely clean. If there's any remnant of your clear liquid on there or clear solid, it can contaminate and affect the next reading. Here you can see the stage is clean and ready for the next sample. Now, Tara is going to test the other samples that we have collected. Here you can just watch her load the sample onto the stage and then go through the process one by one of collecting the refractive index of everything. Remember, when looking inside, you'll see basically that lower half being black. The goal is to have that black part be center of the lens, and you can tell that by a large X in the center of the refractometer. Once you're sure that that black line is centered, you can turn off the light source and then read the refractive index. And always note, you have to take the temperature when doing the refractive index. For your information, the lab is at room temperature, so we can say it's 21 degrees Celsius. Here you can see she is centering the black line. Now she is reading the refractive index. Now that she is done, here is all the collected data for simple distillation. Pause if you need to copy. With simple distillation done, now we can move on to the next part of the lab, fractional distillation. Before we start the experiment, let's do a quick introduction on fractional distillation. Fractional distillation follows the simple application of simple distillation, however, includes a fractionation column. The purpose of this fractionation column is to increase surface area, allowing compounds to cool down and go back into the mixture before reaching the condenser. The result of this is a more controlled distillation, meaning higher purity and better extraction. This is extremely useful and commonly used to process crude oil. Rise in the fractionation column become lower and lower. So basically, if you want to separate lighter compounds, you need a lower temperature, but heavier compounds, you need a higher heat in order to get them through the fractionation column. This thought process is what leads to a higher purity. Now let's start fractional distillation, part 2 of this lab. Tara is starting her sample prep. It is exactly the same as the simple distillation. She's adding her boiling chips and then going to separately measure out the methanol and isopropanol before adding it to the round bottom flask. Note that she's keeping the round bottom flask in the aluminum block to keep it upright. And notice that she's properly measuring her solution in the graduated cylinder. And she will be following the same steps again. Once she measures it out, she will add it to the flask and then mix. And remember, she will parafilm it because these solvents are volatile and can evaporate readily. Remember, she will take out a sample once everything is properly mixed. As you can see, her vial is on the right, ready to go. Here's the new step, preparing the fractionation column. Here you can see Tara is separating the steel wool and packing it into the fractionation column. The more you can pack into the fractionation column, the better the separation. So ensure that it's packed tightly in order to get the best distillation you can. Notice she's using the spatula to help push it down. Without this, she could not properly fill the column. Here you'll watch Tara set up the column and go through the general setup as before. The only new step is adding the fractionation column in between the condenser and the thermometer. The steel wool is being packed tightly, but notice that she is pulling it out and stretching it apart. If it is too tightly packed, the distillation will take too long for it to be effective. So she is trying to fill the fractionation column while ensuring that the surface area is increased, but by not too much. Now that our apparatus is set up, she's getting some tin foil in order to wrap the fractionation column. So remember, we're trying to reduce the temperature in here by increasing the surface area. However, if we allow the temperature to reduce too much, our distillation will not go forward. So we are using the tin foil to wrap and insulate our fractionation column to ensure that it's heated properly. Notice, due to the changed setup, our graduated cylinder is now on a stand. This is necessary to ensure that our sample is collected quickly and does not risk splashing. Here we can see our solution is boiling, and now we are starting to collect our sample. We're observing the temperature and making sure to record it at every 0.5 ml interval. Remember, we are going to collect the first half a milliliter, as that is our first distillate. Remember, when working with the first distillate, to collect it quickly, as both solvents are volatile and can evaporate readily. So quick collection is necessary in order to keep the mixture consistent. And remember, have it in a labeled vial. We have fast forwarded a bit in this distillation to bring you to the end. Here, now that we've collected our full amount, we can now disassemble our apparatus. After disassembling, the samples were collected and run on the refractometer. Please review earlier if you wish to see it again. The data collected for fractional distillation. Remember, it is at 21 degrees Celsius. Now, let's refresh on how to clean up. Here we'll show you what to do with any distillate waste. In the graduated cylinder, we have that mixture. Please place it into the hood in the back and dump it into the large bottle. Any solid waste, aka the boiling chips, can go in the solid waste container in the hood found in the back. These do not need to be rinsed, as the solvents are volatile and will evaporate. Any glass waste is pretty straightforward. Just dispose of it in the glass waste disposal bin. Now that we've finished the experiment, your TA will go over theoretical plates and how to do other calculations in order to determine whether fractional or simple distillation is better. Any other questions, please reach out to your TA. Thanks for listening and have a great day.